Welcome friends. In this module we discuss random variables discrete type. Consider a random experiment of tossing of a coin. The sample space is the set S.C.Gupta HT. Suppose we are interested on the outcome of the toss. It can be H or T. Let x denote the outcome such that x is equal to 1 when H happens and x equal to 0 when tail happens. That is, x of H equal to 1 and x of T equal to 0. Now, x is a real valued function defined from the sample space S. If the coin is unbiased, we get p of x is equal to 1 is equal to p of h, that is equal to 1 by 2, and p of x is equal to 0, that is equal to p of t, that is equal to 1 by 2. For this real valued function x defined from S, if it is possible to define p of x less than or equal to c for any real number c, then the function x is known as a random variable defined over S. For the defined real valued function x, we can write p of x less than or equal to c as p of x less than or equal to c is equal to 0 when c less than 0, that is equal to 1 by 2 when 0 less than or equal to c less than 1, that is equal to 1 when c greater than or equal to 1. Hence, the real valued function x is a random variable. Consider the random experiment of tossing of two dice together. Here we have 36 possible outcomes, that is, the sample space of this experiment contains 36 points as the set containing ordered pairs 1 1, 1 2, 1 3, etc. 6 5, 6 6. Let x denotes the sum of the numbers shown. Then x of 1 1 is equal to 2, x of 1 2 equal to 3, etc. x of 4 5 equal to 9, etc. x of 6 6 equal to 12. You can observe that x is a real valued function defined from the sample space of this experiment with possible values 2, 3, 4, etc. 12. If the given dice are unbiased, the probabilities for various values of x can assign as p of x equal to 2, that is equal to p of 1 1, that is 1 by 36, p of x equal to 3, that is equal to p of 1 2, 2 1, that is equal to 2 by 36, p of x equal to 4, that is equal to p of 1 3, 2 2, 3 1, that is equal to 3 by 36. Proceeding like this, we get p of x equal to 5 equal to 4 by 36, p of x equal to 6, that is equal to 5 by 36, p of x equal to 7, that is equal to 6 by 36, p of x equal to 8, that is equal to 5 by 36, p of x equal to 9, 4 by 36, p of x equal to 10, that is equal to 3 by 36, p of x equal to 11, 2 by 36, and p of x equal to 12, that is equal to 1 by 36. Hence, p of x less than or equal to c can be written for x as p of x less than or equal to c, that is equal to 0 when c less than 2, that is 1 by 36 when 2 less than or equal to c less than 3, that is 3 by 36 when 3 less than or equal to c less than 4, that is equal to 6 by 36 when 4 less than or equal to c less than 5, that is 10 by 36 when 5 less than or equal to c less than 6, that is 15 divided by 36 when 6 less than or equal to c less than 7, that is 21 divided by 36 when 7 less than or equal to c less than 8, that is 26 divided by 36 when 8 less than or equal to c less than 9, that is 30 divided by 36 when 9 less than or equal to c less than 10, that is 33 divided by 36 when 10 less than or equal to c less than 11, and that is 35 divided by 36 when 11 less than or equal to c less than 12, and that is 1 when c greater than or equal to 12. Now, here also p of x less than or equal to c is defined for every real number c. Hence, x is a random variable. As a definition, we can state the random variable or a stochastic variable as a real valued function, say x, defined over the sample space of a random experiment such that the probability statement p of x less than or equal to c is defined for every real number c. Suppose that our experiment consists of observing the life length of a battery surviving 2 years or not. Assume the probability of the battery to survive 2 years is p. let I equal to 1 if the battery survive 2 years and I equal to 0 otherwise. Here I is a random variable. If capital E denotes the event that the battery lasts 2 or more years, then the random variable I is known as the indicator random variable for the event E. Note that I equal 1 or 0 depending on whether E is occurring or not. So far we considered random variables with finite possible values. Consider a coin is tossed till a head turns up and assume x denote the number of tosses required. Here the possible values of x are 1, 2, 3, etc. In this case, the possible values of x are not finite, but countable. A random variable with finite or countable infinite possible values are commonly known as discrete random variable. There exist random variables with uncountable possible values. They are called continuous random variables. Such random variables can take all possible real values between certain limits. For example, 1. A random variable x denoting the life length of a device. 2. A random variable x denoting the waiting time for a bus, etc. Cumulative distribution function. For a random variable x, the function capital F of x that is equal to p of capital X less than or equal to small x for minus infinity less than small x less than plus infinity is known as the cumulative distribution function or simply distribution function of that random variable. Capital F of x denotes the probability that the random variable x takes a value less than or equal to small x. In general, the distribution function capital F of x of a random variable is having the properties: number 1, capital F of x is non-decreasing function of x. Number 2, capital F of infinity that is equal to p of capital X less than infinity that is equal to 1. Number 3, capital F of minus infinity that is equal to p of capital X less than minus infinity that is 0. 4, capital F of x is a right continuous function in the sense that for all x, capital F of x is equal to capital F of x plus that is equal to limit h tend to 0 capital F of x plus h. Let us consider the discrete random variable in detail. Discrete random variable. As we considered earlier, a random variable which can assume only a finite or countable number of possible values is called a discrete random variable. Probability mass function p.m.f. Let capital X is a discrete random variable with possible values x1, x2, etc., xn, etc. Then a function describing the amount or mass of probability distributed at each of the possible values of the random variable is called its probability mass function. As a definition, if x is a discrete random variable which can assume the values x1, x2, etc., xn, etc., then the function p of x or f of x is defined as p of x that is equal to f of x that is equal to p of capital X equal to small x, where small x is equal to x1, x2, etc., xn, etc., is called the probability mass function p.m.f. of capital X. Properties of probability mass function. Let p of x denote the probability mass function of a discrete random variable x, then number 1, p of x greater than or equal to 0 for all values of small x is equal to x1, x2, etc., xn, etc. Number 2, summation over x p of x that is equal to 1. 3, p of a less than or equal to x less than or equal to b that is equal to summation over a less than or equal to x less than or equal to b p of x. Problems. Number 1, an unbiased die with the numbers 1, 2, etc., 6 written on its 6 faces is tossed until an odd number appears. Obtain the probability mass function of the random variable x denoting the total number of tosses required. Solution. Since the die is unbiased, that is probability of the happening of all the 6 faces are equal to 1 by 6, p of odd numbers turns up that is equal to p of occurrence of the sides with the numbers 1 or 3 or 5 that is equal to 3 by 6 that is equal to 1 by 2. So, p of even numbers turns up, that is equal to 1 minus p of odd numbers turns up, that is equal to 1 minus 1 by 2, that is 1 by 2. X denotes the number of tosses required until an odd number appears. Hence, p of capital X equal to small x, that is equal to p of first x minus 1 trials results in even number and x is an odd number. Since trials are independent, we get p of capital X equal to small x, that is equal to 1 by 2 into 1 by 2 into etc. into 1 by 2, that is x minus 1 times into 1 by 2. That is equal to 1 by 2 all raised to x minus 1 into 1 by 2. This implies p of capital X equal to small x, that is equal to 1 by 2 raised to x. We know the number of tosses required for an odd number could be 1, 2, 3, etc. That is, the possible values of x are 1, 2, 3, etc. So, the probability mass function of x can be written as p of x, that is equal to p of capital X equal to small x, that is equal to 1 by 2 raised to x for small x equal to 1, 2, 3, etc. 2. Check whether the following is a probability mass function. Number 1, f of x equal to x minus 2 by 2 for x equal to 1, 2, 3, 4. Number 2, f of x is equal to x square by 25 for x equal to 0, 1, 2, 3, 4. Solution. Number 1. Given f of x is equal to x minus 2 by 2 for x equal to 1, 2, 3, 4. Here f of 1 equal to 1 minus 2 by 2, that is equal to minus 1 by 2, which is not divisible, because by the property of probability mass function, f of x greater than or equal to 0 for all x. So, the given function is not a probability mass function. Number 2. Given f of x is equal to x square divided by 25 for x equal to 0, 1, 2, 3, 4. Here f of 1 equal to 1 square by 25, that is equal to 1 by 25, f of 2 equal to 2 square by 25, that is 4 by 25, f of 3 equal to 3 square by 25, that is 9 by 25, and f of 4 equal to 4 square by 25, that is 16 divided by 25. F of x greater than or equal to 0 for all x. Then f of x satisfies the first property of p.m.f. Summation over x f of x is equal to 1 by 25 plus 4 by 25 plus 9 by 25 plus 16 by 25, that is equal to 30 divided by 25, which is greater than 1. Here f of x failed to satisfy the second property. Hence, it cannot be a probability mass function. 3. Given a discrete random variable x with probability distribution as the values of x 0, 1, 2, 3 and 4 corresponding f of x values 0.2, k, 2k, k by 2 and 0.1. Number 1, find the value of k. Number 2, find p of 1 less than or equal to x less than or equal to 3. Solution. Number 1, for a probability mass function f of x, we have summation over x f of x that is equal to 1. So, here 0.2 plus k plus 2k plus k by 2 plus 0.1, that is equal to 1. This implies 3k plus k by 2 is equal to 0.7. This implies k is equal to 0.2. Number 2, we have p of a less than or equal to x less than or equal to b, that is equal to summation over a less than or equal to x less than or equal to b f of x. Hence, p of 1 less than or equal to x less than or equal to 3, that is equal to summation over 1 less than or equal to x less than or equal to 3 f of x, that is equal to f of 1 plus f of 2 plus f of 3. This implies p of 1 less than or equal to x less than or equal to 3, that is equal to k plus 2k plus k by 2, that is equal to 7k divided by 2, that is equal to 7 into 0.2 divided by 2, that is equal to 0.7. Cumulative distribution function or distribution function of a discrete random variable. Consider the case of a discrete random variable x with the probability mass function f of x is equal to 1 by 2 when x equal to 0, 1 and equal to 0 otherwise. From the given probability mass function, it is clear that the random variable can assume only two values 0 and 1 with p of x is equal to 0, that is equal to 1 by 2 and p of x is equal to 1, that is equal to 1 by 2. The graph of the p.m.f, which is a point function, can be sketched as follows. It can observe that there are no possible values for x less than 0. Hence, p of x less than 0 equal to 0, or we can write p of x less than or equal to small x equal to 0 when small x less than 0. At the value 0, x has a probability 1 by 2. Therefore, p of x less than or equal to 0, that is equal to p of x less than 0 plus p of x equal to 0, that is equal to 0 plus 1 by 2, that is equal to 1 by 2. The next possible value of x is 1. Therefore, p of x less than or equal to small x, that is equal to 1 by 2 when 0 less than or equal to small x less than 1. At the value 1, the probability is 1 by 2. Hence, when x is equal to 1, p of x less than or equal to 1, that is equal to p of x less than 1 plus p of x is equal to 1, that is equal to 1 by 2 plus 1 by 2, that is 1. There are no other values for x. Therefore, p of x less than or equal to small x is equal to 1 when small x greater than or equal to 1. Hence, the cumulative distribution function of x, capital F of x, that is equal to p of capital X less than or equal to small x, can be summarized as capital F of x is equal to p of capital X less than or equal to small x, that is equal to 0 when small x less than 0, that is equal to 1 by 2 when 0 less than or equal to small x less than 1, and that is equal to 1 when x greater than or equal to 1. The graph of capital F of x is a step function having discontinuity at the points 0 and 1. At these 2 points, the function capital F of x is having jumps of magnitude 1 by 2 each, which is equivalent to the probability distributed at these points. Properties of distribution function capital F of x. Number 1, capital F of x greater than or equal to 0 for all x belong to R. Number 2, capital F of x is non-decreasing, that is capital F of x greater than or equal to capital F of y if x greater than or equal to y. Number 3, capital F of minus infinity, that is equal to 0, capital F of plus infinity, that is equal to 1. Number 4, p of a less than x less than or equal to b, that is equal to capital F of b minus capital F of a. P of a less than or equal to x less than or equal to b, that is equal to capital F of b minus capital F of a plus p of x is equal to a. P of a less than or equal to x less than b, that is equal to capital F of b minus capital F of a plus p of x is equal to a minus p of x is equal to b. Number 5, capital F of x is a step function which ensures the right continuity of function. Problems. Number 1, find the distribution function capital F of x of the random variable x with the following probability distribution. The values of x 0, 1 and 4 corresponding small f of x values 1 by 5, 2 by 5 and 2 by 5. Solution. For the random variable x, the possible values are 0, 1 and 4 from the given probability distribution p of x less than or equal to small x, that is equal to 0 when small x less than 0. 0 is a possible value of x with probability 1 by 5. Hence, p of x less than or equal to 0, that is equal to 1 by 5. The next possible value of x is 1 with a probability 2 by 5. Then p of x less than or equal to small x, that is equal to 3 by 5 when 0 less than or equal to x less than 1. The next possible value of x is 4 with a probability 2 by 5. Then p of x less than or equal to small x, that is equal to 1 when small x greater than or equal to 4. Now, the distribution function capital F of x is capital F of x, that is equal to p of capital X less than or equal to small x, that is 0 when small x less than 0, 1 by 5 when 0 less than or equal to small x less than 1, 3 by 5 when 1 less than or equal to small x less than 4, and 1 when small x greater than or equal to 4. 2. Given the distribution function of a discrete random variable x, find the probability distribution of x. Capital F of x is equal to 0 when x less than minus 1, that is equal to 1 by 3 when minus 1 less than or equal to x less than 0, that is equal to 2 by 3 when 0 less than or equal to x less than 5, and 1 when x greater than or equal to 5. Solution. Given distribution function capital F of x is a step function. For a discrete random variable, the possible values of the random variable are the stepping points of its distribution function. In the given capital F of x, the stepping points are minus 1, 0 and 5. The magnitude of the step of capital F of x at a stepping point is the corresponding probability mass at that point. At x equal to minus 1, the value of capital F of x jumps to 1 by 3 from 0. Then the magnitude of step at minus 1 is 1 by 3. This gives probability of x is equal to minus 1, that is equal to 1 by 3. At x equal to 0, the value of capital F of x jumps to 2 by 3 from 1 by 3. Then the magnitude of step at 0 is 1 by 3. This gives p of x is equal to 0, that is equal to 1 by 3. At x equal to 5, the value of capital F of x jumps to 1 from 2 by 3. Then the magnitude of step at 5 is 1 by 3. This gives p of x is equal to 5, that is equal to 1 by 3. Hence, the probability distribution of x is x values minus 1, 0 and 5 corresponding f of x values 1 by 3, 1 by 3 and 1 by 3. Number 3. For a discrete random variable x, capital F of x is given by capital F of x is equal to 0 when x less than 1, that is equal to 3 by 8 when 1 less than or equal to x less than 2, 5 by 8 when 2 less than or equal to x less than 3 and 1 when x greater than or equal to 3. Find p of x greater than 2, p of 1.5 less than x less than or equal to 2. Solution 1. We have p of a less than x less than or equal to b, that is equal to capital F of b minus capital F of a. Then p of 1.5 less than x less than or equal to 2, that is equal to capital F of 2 minus capital F of 1.5. This implies p of 1.5 less than x less than or equal to 2, that is equal to 5 by 8 minus 3 by 8, that is equal to 2 by 8, which is 1 by 4. P of x greater than 2, that is equal to 1 minus p of x less than or equal to 2. This gives p of x greater than 2 equal to 1 minus capital F of 2, that is equal to 1 minus 5 by 8, that is 3 by 8. It's time to summarize the session. In this module, the concept of a random variable is introduced. This module is concentrating on discrete random variable. The idea of probability mass function p.m.f. and cumulative distribution function of a discrete random variable is narrated. Properties of p.m.f. and distribution function are discussed. Some problems in connection with the above concepts are solved to get a better grasp of the concepts described. Questions to be answered are: number 1. Suppose a coin having 0.7 of coming up heads is tossed 3 times. Let x denotes the number of heads that appear in the 3 tosses. Determine the probability mass function of x. 2. For a random variable x, the probability mass function is small f of x is equal to x divided by 15, where x is equal to 1, 2, 3, 4, 5 and f of x equal to 0 elsewhere. Number 1, find capital F of x. Number 2, find p of 2 less than or equal to x less than or equal to 5 by 2. Find k if small f of x is equal to k into 2 by 3 raised to x for x equal to 1, 2, etc. is a probability mass function. 4. The distribution function of a random variable x is given as capital F of x is equal to 0 when x less than 0, 1 by 8 when 0 less than or equal to x less than 1, 3 by 8 when 1 less than or equal to x less than 2, 5 by 8 when 2 less than or equal to x less than 5 and 1 when x greater than or equal to 5. Number 1, draw the graph of capital F of x. 2. Determine the probability distribution of x. 3. Evaluate p of 0.5 less than x less than or equal to 4. The books for your references. Number 1, Sheldon M. Ross, Introduction to Probability Models, Academic Press 1997. S.C.Gupta, V.K.Kapoor, Introduction to Mathematical Statistics, Sulthan and Sons, 2003. T.K. Chandra, D. Chatterjee, A First Course in Probability, Narosa, 2003. S.M. Ross, A First Course in Probability, Pearson Education, 2007. R.A. Johnson, Probability and Statistics for Engineers, PHI, 2005. Hope you enjoyed this session. See you next time. Until then, goodbye.